folks.
I'll only get halfway through.
Was that microphone to be radioactive?
It was not.
Okay, we'll get started. As most of you know, I'm Steve Cox. I'm the board president here at the museum. We just have a couple of non-member guests, but thank you all for coming out today. This is going to be a very nice talk. Our speaker today is Neal Farmer, currently with the Idaho Department of Water Resources, where he has published numerous articles on the hydrogeology of the Eastern Snake Plain Aquifer, and also how the springs all along the Snake River work. Before that, he was with the National Park Service and was doing work on radioactive minerals and fossils at the Hagerman fossil beds. Very interesting, and maybe we'll hear a little bit about that too. To allay any concerns, we did scan Neal, and he is only emitting at background levels. So let's give a big hand for Neal Farmer.
Thank you, everyone. Appreciate your time and attention. And it's the first time I've been here, so it's quite an honor and a lot of interesting rocks and minerals out here to look at. I guess a little bit about my background first is I was born and raised in Twin Falls, Idaho, and lived in Idaho my whole life. Went to college at CSI in Twin Falls, and then University of Idaho for my bachelor's in geology, and then they couldn't get rid of me, so I stayed around and did my master's in geology at U of I also, and some of my work experience up at the U of I actually kind of plugged me into this particular topic of interest. As mentioning earlier, I got about halfway through the story, and when I was working up there, I was working for the Hazardous Waste Remediation Center, and we were digging out gas and diesel fuel spills down around Sweet Avenue and over at the farm area. And we ran across a nice cut-fill sand, granitic sand field, it's just loaded with mica. So I took a sample of it to Earl Bennett, and he said it would be interesting if you could get a nice concentration of mica and then shoot it with a Geiger counter and see if it's hot or not. And if it's not, it'd be from Roscoe Mountain. If it is, it's probably from Paradise Ridge to the south, so source areas for the sedimentations. So I did, and it wasn't hot, or at least above background. But when I had the Geiger counter, it was kind of handy back in my apartment, along with all the other piles of rocks. I started going across all my rocks and everything, and I got to a mastodon molar tooth that I found down at the Hagerman fossil beds back in the late 1980s, and pegged the needle, went off the scale, radioactivity. And so I was like, oh wow, that's kind of cool. Well, just the following year or two after that, I got a job down at the fossil beds, a seasonal position, actually doing archaeology. And when I was down there to the paleontologist, I said, hey, I have this mastodon tooth, and went out with radioactivity, Geiger counter. I said, how about if we check some of the stuff in collections? And that's the connection that started this whole deal. Actually, for me, it started back in the 1980s, informally, but formally with my job position, and it's carried on well through the 90s and 2000s and into today's. Pardon me, I got a little frog in my throat, like maybe some others here mentioned. I was sanding a shovel handle down that I broke yesterday, shoveling dirt, crushed my toe. But so This is, the presentation will cover several elements. You may have already read about them. Some's gonna be, radioactive fossils, which is, you know, kind of the real most interesting part of it. The other part's just ionizing radiation. It's kind of default to keep in this, because I don't know really the backgrounds. You folks probably know a lot more, but, you know, with water resources, nobody knows anything about radioactivity and some other audiences I've had, so I've included that. But and then some analyses we've done, both mapping and stratigraphy mapping relative to the radioactivity and the fossil deposits. It was a cursory scoping level, so there's not a lot of detail. And then also some connection with Idaho's Plow Share project, or not Idaho's, but Idaho's connection to the Plow Share project, which is an atomic energy program. And that's about it. Are there any questions right at the moment before we get rolling or anything? I do currently work for the Idaho Water Resources. I've been there for 15 years. Mostly groundwater digesters. We've done green stuff, not radioactive green stuff, but safe green stuff, forcing into groundwater track where it goes on the Eastern Snake Plain Aquifer. And we've done about 25 of those traces in the last 13 years with some incredible results for groundwater velocities and things like that. Yes.
Yeah, I was gonna say that what they find that was actually yielding, what was the source of that radioactive material?
For this,
Yeah,
we'll get into
okay, that's all right. I
that.
did.
But the bottom line, I worked for the Hagerman fossil beds for 11 years and finally quit the feds and worked for the state. A lot of people do the reverse, but it's not what I do. So, Lake Idaho existed in southern Idaho, roughly in this stippled or patterned area of blue, extended out into Oregon, and the eastern shore of Lake Idaho was in the Hagerman fossil beds area. And because of that, it is in the deltaic and floodplain margin area of the lake. And it existed from about 5 to 1.5 million years ago. Mostly land vertebrate fossil assemblage, so as you get towards Glens Ferry, you're getting more into the lake proper. So you pick up a lot more fish fossils and things like that. But on the eastern shore, we had a wide variety of fossils, critters that are still around today, you know, ducks and geese and otters and things of that in these floodplain environments. But there were a lot of critters that aren't around today, like sloths and saber-toothed cats and mastodons. And a zebra-like horse, they call it a zebra-like because it had the same skeletal bone structure similar to modern-day zebras, so kind of stocky. And the landscape back then was much more temperate, kind of like southeastern United States. Warmer winters and cooler summers. And part of the reason for that is the coastal mountain range and volcanoes hadn't risen high enough to create the rain shadow effect and the desertification of the area. But the lake was about 50 miles wide and 150 miles long, comparable to Lake Ontario back in the Great Lakes area. And so it's quite a large lake. One thing a lot of people don't know before I move on is that the sediments are exposed in the Hagerman Valley, of course, and dominantly on the western side of Hagerman Valley. But over on the eastern side of the Hagerman Valley, they're also exposed, and just not as well. And I've done a lot of work for the Department of Water Resources. In fact, that's one reason why they hired me, is because I'd already studied the lake bed sediments on the west side so much, and they were interested in the geologic controls of springs from the East Snake Plain Aquifer, Niagara Springs, Clear Springs, Thousand Springs, etc. And why they occur, where they do, and their spatial distribution and discharge patterns. And so that was one of the items they hired me for, is to look into that subsurface environment and those controls on the springs. So I've been doing that for 15 years, or off and on. There's been like 3 years where I haven't even touched it, busy with other projects. But my point is that we have mapped those subsurface lake bed sediments eastward underneath the basalts, the quaternary basalts, out to the Jerome area. So they're all still there. They're just buried with basalts and haven't been exposed like they are in the Hagerman Valley. And so what it does for the aquifer is it creates a wedge of clay into the middle of the aquifer, and some of the aquifer diverts underneath it, some flows over the top of it. And that's a huge, major hydrogeologic disconformity when you're trying to model the groundwater system of that area. This is just some photos there on the Hagerman fossil beds and the formations. These are, of course, again, floodplain units, and they'll be encased stream channels. The grayness is a fine sand, fluvial nature that's encased in these floodplain silty clays. They're dominantly silty clays in the formation. 70+% of them are just silty clays. And they have these repetition layers. They're very repetitive in the USGS documents. They even note the word monotonously repetitious. And they're upward fining, and they're capped by these little dark layers, which are carbonaceous paper shales. So in your floodplain environment, you have this flood event, you get the coarser material drops out first, and then of course the finer and finer material until at the very end you get all the organics dropping out. And so those organics are those carbonaceous paper shales that cap each one of those floodplain units. It is the Glens Ferry formation, just for note, and then it's capped with the Tuana gravel formation up on top, which represents the draining of Lake Idaho, and all the rivers were then starting to flow across the lake bed sediments and depositing gravels. And this volunteer was helping excavate and remove a camel femur right there from the Tuana gravel. And I kind of show this because we did some study, some of the radioactive study of, Glens Ferry versus Tuana in these natures vertically. So, the officially designated by the legislature, Idaho State fossil is the Hagerman fossil bed, the zebra-like horse. And a rancher down in the area, Elmer Cook, back in the 30s, was herding his cows and sheep out on the monument. And he saw some bones laying on the ground and picked them up. And he heard that Harold Stearns, who works for the USGS back in the 1930s, was traveling through on the railroad. And so he took him up to Bliss and met Harold. And Harold then took those fossils back to the Smithsonian Institution. And for numerous years after that, in the late 1930s, the Smithsonian Institution came out and started digging up fossils. And this is one of the bone beds of the actual horse quarry site on the monument. And they did it the old-fashioned way, shovels and horses and also dynamite. Because this is a cemented fossil bed layer, and it's just like concrete, basically. And so trying to remove those fossils was quite difficult in the field and time-consuming. So to expedite the field portion of their activities, they just used dynamite. Blow it up, pick up the chunks, and haul them back. And Now, you might think that that's, those types of methodologies were antiquated and not done anymore. But when I worked for the Park Service, the Park Service got some money, funding, to go in and excavate, re-excavate, open up the horse quarry again. That was in the late 1990s. And so you might think, well, we do a much better job nowadays because we're much more educated and conscientious. No, they went in with a backhoe and just scraped it off as much as possible, and they broke out all kinds of fossil material to remove all the overburden, and just scraped and broke and cut fossils like crazy. In fact, for years and years, we had a big chunk of fossil piece, just like this, cemented, sitting in the visitor center. And if you look close, it was just sheared on all sides because they busted it out. And if anybody would have went, how come this is all broken? But nobody ever asked that. But the backstory for us that worked there, we knew. And the reason it was on display in the visitor center is because they didn't know where it came from. It was broken. So it was kind of like this piece that was out of context. So it was, put it in the visitor center. And I don't know if that's still on display or not. But if it is down there, walk up to them and go, yeah, this is all sheared off on all sides. Like it's just busted out or something. Now you know, and there's scrape marks across the top where the buckle back was scraping across it. So, at any rate, yeah, I observed that firsthand. Just scale, there's some rib cages partially articulated, some tools here for scale, rather. Pelvis, of course. Here's a skull. Here's the brain case, 2 eye sockets, and then the snout right in here. A femur sticking up there if you can see it. Mostly partially articulated, so it would be like chunks of the horses were all still together, like the rib cage or something, but not like the entire animal. So,
what was the reason for the bone bed? I mean, what?
Well, that's a good question. Nobody's ever found out, but it is in a sand unit. So it's a old river channel with a lot of cross bedding, about a medium to fine sand, not terribly coarse material, fairly fine. There's been over 200 individuals found. Again, that wasn't 200 complete skeletons, but if you find 200 skulls, you know there are 200 individuals there. They have postulated, and probably nobody will ever really know, but similar to modern day, an analogy for modern day is like in Africa when a herd of wildebeests or something cross a river, they can panic, drown, and float downstream into a log jam of dead bodies, basically, possibly. And all different ages are present, so, you know, the youngsters and the old ones, they're all there. So it's like the whole herd died in the river. So
the sediments were really where they were getting trapped?
Well, I don't think so. I mean, I'm not aware that anybody's seen any evidence of trapping in the sediments. You know, like quicksand.
Yeah, well, I mean, just something they just get bogged down. and
Yeah.
stuck.
I don't think they ever found any that were vertical in nature. I don't know if you got bogged down. I think there'd be a lot of verticalness in the limb bones, especially. But these are all pretty much been horizontal layer, like they've been moved, and very little carnivore evidence. So
They buried it pretty fast.
yeah, probably buried pretty fast. So not much evidence of scavenging carnivores and things, you know, picking on the bones and stuff. Yeah, it's kind of interesting. Paleontologists can certainly go into that a lot more, but we've had a lot of turnover down there in the last few years. Yep.
What's
what's the tool? You got tools.
There's a pick, there's the handle there, just a pick, so, I don't know.
But not
Jab.
part of the horses. Not part of the horse's burial.
No. No. This is part of the excavation process for the gentlemen that were out there. Hammers, tools, chisels, I suppose, probably anything to get those fossils out of there. But these are radioactive, and this is the official site here for the Idaho State Forest, and back in the 30s. On our field meter would register about 3,000 counts per minute radiation. That's decays per minute, so 3,000 radioactive decays per minute for field testing on that. Charles Steen is kind of interesting. I mention this because you may know his story. I'm sure there's some folks in here. There's some couple documentaries on his story. He was basically kind of an out-of-work geologist, dirt poor in southern Utah, living in a tar paper shack. And here's a photo of his residence at one time. And in the 1950s, during the Cold War years, the U.S. government did not have a significant domestic source of uranium for bombs, and so they felt insecure, kind of like today with lithium for our batteries. We're relying on China and Australia for the main lithium sources. And so they would put out announcements and things of that nature, and basically recruiting the civilian population that, hey, when you take your family out picnicking or deer hunting or whatever, out, take a Geiger counter with you and, shoot the rocks while you're out there, because they needed to find a source of uranium, a significant source. So there was a big push for discovering uranium, and Charles Steen did discover some. He used his geologic knowledge to look for it where other people had not looked for it. And those were in some sandstones and anticlinal structures in southern Utah. And that's what we have down at Hagerman fossil beds, is in the sand units. We'll get into that. That's where the radioactivity is coming from in the fossils. He made millions of dollars off his discovery. He lost most of it, but he was also a philanthropist. He gave a lot of money, bought land and gave it to schools and churches and things like that. And I always put this in here. He died of Alzheimer's in 2006. I would have anticipated cancer myself, but that's just me. So, at any rate, and some of the deposits he found were kind of a blackish deposit. So, this is where I digress a little bit from Charles' story to natural nuclear reactors, which I didn't know there were any until I'd done a little more background work. But over in Africa, in the Gabon region, there's been some nuclear reactors that were natural. And so the uranium that was deposited in these delta systems from river deposits, just like at Hagerman, the uranium concentrated enough, up to 60%, that they went nuclear by themselves. And there's several of those. In fact, uranium-235 is 4 times the concentration than in modern nuclear power plants. They were hot. Yeah. And they ran for, well, they have here, 600 to 800,000 years. But I add this in there because some of the geology is basically the same theory behind why is the radioactive deposits in the Hagerman area occurring, and possibly it's from rain-washed uranium minerals being deposited along the eastern shore of Lake Idaho. And this is a photo of those natural nuclear reactors. There's somebody standing right here for scale. And of course, I think you can see that person there, but they're a black deposit, they've been cooked. These are sandstones. And this is just a source of this information if you want to look it up or something. So, back to Hagerman. This is a Hagerman horse hoof. This is the horse hoof here, and one of the phalanges here. And then Borophagus, which was a hyena-like dog that was present back then. Some beaver vertebrae, and a horse tooth from the Hagerman horse quarry site. And if you notice, it's kind of gray color in here, and that's one thing we started to look for in the field for radioactive fossils. It had a lot of gray coloration. But they would, again, about 3,000 CPMs. Background radiation is about 40. So if you just held it in the air or something, you'll get about 40. But there's other stuff. This is just fun photos more than anything. And you notice this photo, this is a turtle shell breastplate area, underside, and it only has 40 CPM, which is back. So basically it doesn't have any. So why would the horse quarry have such high radioactive emissions, and then maybe a turtle doesn't? And if you notice, it's brown instead of gray. And the light colored areas here, that's from sun bleaching. Those were the pieces that were laying on the ground. And then the darker were the pieces underground that we excavated. Gastropods, salmon, vertebrae, fur pollen, and water lily, and diatoms all suggest, a more temperate climate. It's warmer and wetter. Water lilies like to grow, in a more southern climate area. And firs, of course, there are conifers on the landscape down in that area. And this microtine, I call them rat teeth, but bowls and bowls, gobs of those. They collect, the paleontologists collect tons of those things. These are museums all across the United States that have Hagerman horse quarry specimens in their collections. And so all of those museums have radioactive fossils in their collections. It's well known in the museum industry. Everybody has some radioactive stuff, something naturally. So we decided to do a little study, and it's a scoping level. Wasn't real intense by any means, but we went through the collections area with just a surface Geiger-Muller counter and checked over 300 specimens, and in our storage, 75% of those specimens had at least twice the natural background or higher, so roughly 80 CPM or higher. 136 of those 300 specimens were 1,500 to 21,000. The hottest specimen was 21,000 counts per minute, and that was a peccary phalange, one of the wild pig phalange, and the little knowledge about. Now we did not include all the horse quarry stuff because there's so much of it would bias the sample. So we said, it's basically one site, one sample, because it was pretty much all the same. So we went and checked everything else and added right in. That way we didn't bias it by all the material from the horse quarry. These are horse jaws right here that Mary's zapping with the Geiger counter. Now, if you know about Geiger counters, they're not very efficient. They're only about 30% efficient. So of the beta emission from a radioactive specimen, only about 30% actually get registered on a Geiger counter, so 70% of it doesn't even get registered. So when you have a count of 21,000, that's only 30% of the actual emission. Geiger counters primarily respond to beta. They don't respond well to alpha or gamma, so they have alpha, beta, and gamma emissions. And we'll get into those just a little bit more here in a sec. And so alpha is a very large particle, and usually the sensor has a cover on it, a face of some kind, and that face will block the alpha. And your skin will block it, and a piece of paper will block it. And gamma is so high energy that the sensor doesn't pick it up. So with this particular meter, according to the manufacturer, you'd only pick up about 1%, 2%, 3% of the alpha and gamma, but it's dominantly the beta emission or the electrons off the atom that pick up. So there's a lot more emission that you're not detecting. This was just a report by the USGS in 1954, Smith and Bradley, and they were reporting on some fossil material, uranium content that they had found. And I just added in over here. So they published this, and they had, 200 counts per minute. We have 21,000. So the whole point is, here's something that 200 counts per minute is publishable, and we have a lot more than that. So almost, at least an order of magnitude more. And we've had some other studies done. We were looking at this earlier. Dr. Mickey Gunter, University of Idaho, did some analysis using X-ray fluorescence and some SEM, EDS, XRD analysis, which is kind of a scoping level. And then he published some of the results at GSA in 2005, just for reference. But he did find that the carbonate fluoroapatite and the fluoroapatite mineralization were holding some of the radioactivity. If I remember correctly, the calcium item has the same ionic radii as uranium. I think that's close, if I remember correctly. And so it fits in there nicely in the mineral lattice structure. And it's kind of like your shoes, they gotta fit. And so that uranium atom will fit into that mineral lattice structure nicely, where other atoms won't, because of the ionic radii. So during the fossilization process, as the material is converting from organic matter based, us, our flesh and bones, to mineral, those minerals are growing, and during that transition from the critter to a fossil, the uranium is being transported in and incorporated into the mineral lattice structure. And so the question is, where did the uranium come from? What was the source of it? And so there's been a lot of discussions about that, but nobody's ever chased that. There's a master's thesis right there. And he identified uranium and thorium. There's a whole suite of radioactive isotopes present. We'll get to that in a second. But uranium and thorium concentrations are high. And this is all Mickey Gunter's observations, and that here he's talked about what I've just talked about, also about substitution of the apatite phases and absorption on the mineral surfaces, things of that nature. These are the radioactive isotopes here with these numbers. So we had uranium identified, and thorium, and radium, and lead. radioactive lead, bismuth, and cesium, and protactinium, as well as a bunch of other rare earth elements that are included in the analyses. Does anyone see anything wrong or out of order in that list of radioactive isotopes? There's something that doesn't fit. The proverbial, what's wrong with this picture? I'll wait.
Where did the barium come from?
Yeah, well, I'm not sure about some of the rare ones, but out of the radioactive isotopes in particular, is what I'm referring to.
The cesium bothers me.
Yep, that's it. First person to ever get it in any of my presentations.
Because I'm just starting to mind a little.
Yeah, it's man-made.
Yeah.
It comes from bombs.
Yeah.
So, we detected cesium in this, and so it's kind of interesting. You know, these fossils are, what was the age of these fossils I just said? Let's see here.
Just seriously,
A couple million years, yeah, 3.5 million. And so how does cesium, from the 1950s or 60s get incorporated? And it's probably just transported in, so it's made its way through the overburden
I
soil.
kind of wondered how it got involved in
Yeah, and so it's something that's basically a post-fossilization process that's occurred and transported into the subsurface and deposited on probably the surface of the fossils. Rainwaters and things like that.
I know nothing about this, but I'm gonna throw something out. What about the natural reactors? Do they create cesium?
No. Cesium is only created under, it's, as far as I've been told, dominantly only human created, so it's anthropogenic.
Why was its number so low compared to the other reactors?
The isotope number,
Yeah.
I guess just where it falls in the.
That's the periodic table, that's the periodic table distance.
Yeah, if you wanna go get a chemical chart.
Sorry, I have it right here, but. it's-
Let's do that afterwards.
I just wanted an easy answer.
Oh, come on.
Yeah.
Get it for
So,
you.
number of neutrons and protons, it's the isotope. Yeah, and so so we had some analyses done by the University of Idaho, but also the Uranium Registry by WSU and Data Company in 1997 to identify these items here, and these were some of the results of that.
And they weren't looking for potassium?
It wasn't in the outcome, or was it, as far as I know, it wasn't. They may have, the stuff that I listed up here, I was mostly interested in the rare earths,
Yeah.
lanthanide series, and of course the isotopes, but I don't know what the full suite was. I'd have to pull out the analyses. Maybe potassium is in it.
But I mean, it is radioactive.
Yeah, can be.
Yeah, okay.
But it certainly wasn't identified as a radioactive isotope. I can confirm that. Yeah. For the radioactive isotope of potassium. So, after we got done analyzing the fossils for radioactivity, we said, well, what about something else out there, like the geologic deposits? And so we ran around out on the monument, zapping everything we could with the Geiger counter. This is the basal portion of an interbedded basalt flow, lava flow, in the lake bed sediments, and that this basal portion is a rubble zone, and it was a little warm, 300 to 400 counts per minute. Again, background would be 40 to 50 range. So there was a little bit of radioactive deposits in that. This would be, a 3.5 to 4 million year old lava flow, the same age as the fossils. So we also went and checked some of the volcanic ashes. And this is an ash over here, and then also some of the carbonaceous paper shale units that I was mentioning earlier, which is here. And all these little black spots are carbon impression, carbon fossils, chunks of cattails or whatever.
Vegetation, basically.
Yeah, vegetation. Yeah. But they both ran in the 300 counts per minute, which is about an order of magnitude above natural background. So then we decided, well, we know all the fossil sites where they're at, and we'd already checked everything in collections. Now all we have to do is create a map of where the radioactive sites are on the monument. And so this is the snake. This is a elevation DEM base. So this is all elevation based map. This is the Snake River run along here. Then you have about 600 feet in elevation rise up to the top of the plateau over here. And then these are all canyons cut into those horizontal lake bed sediments. And these are mapped fossil sites and the amount of radioactivity associated with those. There's the Peccary site over here. But we also looked at some of the salts. There's one salt up in here. The horse quarry is located up here in this zone. And then we looked at the base of the salt down below, low in the section, geologic section, and it was only registering at 40, which is background.
So a lot of that material just flowed through and wasn't captured by the material except the bones. So it concentrated it.
Yeah, the bones definitely concentrated, and they concentrated it because organic material acts like a sponge. It's through chelation is the process, and so naturally the uranium atoms naturally are attracted, kind of like static electricity or something, to that material, and so the chelation process kind of sucks them in for that organic matter. So we looked at it horizontally here, the spatial distribution, and then we said, well, let's look at it vertically because we knew all the elevations of everything. And so this is a vertical look at the distribution or the propensity or the number of radioactive sites. And this is in meters, unfortunately, but the Snake River is located down low and the top of the plateau located up high. There's about 600-foot elevation change in this range. And so you can see the number of fossil sites increases, like for here, for radioactive presence. And the trends associated in here were about the lower half of these bed sediments have much more radioactive fossils than the upper half of the lake bed sediments. And why, I'm not sure. This was, again, was just a scoping level investigation. We just went in and quickly looked at everything, but that was some of the relationships that we found. And then the salt flow I showed earlier that had some radioactivity is located about halfway in that package of sediments. And the one that didn't have any radioactivity is clear down here at the bottom. So why? I don't know. But those are some of the relationships spatially, horizontal and vertical. Yeah, so in summary, 130 radioactive fossil sites documented so far. 50%, more importantly, are 1500 CPM or higher. Those are pretty hot. And it is, of course, the official state fossil. But geologically, all of the radioactive fossil sites and fossils from those sites were in permeable sand units, just like the natural nuclear reactors, and also Charles Steens' discovery.
Yeah, I'm just thinking, did you ever find any low front uranium deposits?
No,
You haven't found any?
No.
Okay, I just.
no, dominantly just in the fossil material with some low levels in some of the other geologic deposits.
Yeah.
Yeah, but nothing like Charles Steen found or so it's in the fossils, and the fossils are that are radioactive are coming from the sand units that are permeable, which suggests that during that fossilization process, the waters are carrying in uranium.
There you go.
And so then it begs the question, well, where is it coming from? And so source areas for the sediments has always been of interest to the sedimentologists and the paleontologists. Where were the rivers coming from, the highlands? Where was this transport mechanism or the drainage pattern coming into the lake? And so this could provide some clues because from what I've heard anyway, and I actually don't have any documentation on this, the pink granites up around Sun Valley are a little bit warm in radioactivity. And so that drainage pattern of the Big Wood River system, the Wood River, et cetera, or in that area could have been the source area dissolving up those uranium atoms and transporting them down. We don't know, but that's the best that we've theorized so far. So we presented this in 2005 at a Great Rift Science Symposium, abstract and in-person presentation. It's also published now in the Journal of Environmental Radioactivity back in 2008 or 7. I think 2008. You can search that online. That's a copyrighted publication, so I can't provide copies of that. But it is out there. We were able to fortunately get Dr. Ron Catherine as one of our authors, and he's a heavy hitter in nuclear science, but he's written a lot of textbooks and taught at universities, WSU and stuff, which really helped us out. Analyzing and determining the effects of human health and safety element of this. And the fossil beds used to have a program called Camp Pliocene, 2001, and they would issue a fossil record, which was a little newsletter, probably quarterly, they would fall 2020, 2001, of all the activities going on in fossil beds. And they commonly, for this Camp Pliocene, would bring bus loads of kids out to the fossil beds, and they'd let them go pick up all the scraps that would be busted out. And there they are holding a bunch of these radioactive fossils. So I think they stopped it. But there's a whole bunch of backstories on all this.
No, the pink granite, what was the source of that pink granite?
I believe they're up in the Sun Valley area. Yeah, so it's part of the batholith. Yeah. Yeah.
So Neal, has there ever been any work done to figure out what the source of the radioactivity is in general? I mean, when you take a look at, for example, oral analysis in oceanic sediments, you can usually tell, oh, you've got gamma rays or this energy, and based on that, you know that it's coming from potassium out of narcotic kind of thing. There's quite a bit you can get out of that. I know that like Baker Martin makes lots of instruments to drop down boreholes. Yeah. So.
Well, we had lab analysis done to identify the isotopes.
Yeah.
And so all those are radioactive and emitting either alpha, beta, gamma, or a combination thereof. And and that, I think those analyses were only for the Hagerman fossil beds, the horse course site.
Yeah.
But yeah, it's just based on that analysis that was done for the horse course site. So other than that, I guess not. So this is a little learning exercise about radiation. based on some previous work. And so you have particulate and then electromagnetic. And particulate radiation, you get your alpha and beta particles, and then your electromagnetic radiation, or EM, like X-rays and gamma rays and things, right? And alpha particles are large particles of a helium nucleus, so they're a big particle, and they're dominantly blocked, easily blocked by a piece of paper or even your skin, but you can breathe them in pretty easy. And we'll get to that in a second. That's alpha. Beta are electrons being emitted off of the isotope, and they're kind of an internal hazard, also external because they're higher energy, and so they can blast right through a piece of paper or something quite easily, but some of them do get blocked. X-rays and gamma rays, that's kind of like the sun. You go outside and get exposed to EM, but then when you remove from the sun, you're no longer exposed to it. And they're primarily an external hazard, so you don't breathe in sunlight. It's on your skin and stuff, or even your eyes. So a little backstory on radium. Radium was identified in the fossils down at Hagerman, and these were the radium watchmaker dial painters back in, especially during World War II. But radium was originally discovered by Marie Curie, in 1838. And her husband, and also and they have a half-life of about 1,600 years. And so they found out that the ionizing radiation, or radiation emitted from radium, would excite the electrons on fluorescent compounds. And so they call that radioluminescence. And so they would mix radioactive material with these fluorescent compounds.
Yeah.
And so they would spontaneously give off light. And then they would have this little mixture that they painted on these dials so that you could see them in the dark and you didn't have to have a light to turn on. And so the ladies that were doing this, especially during World War II, would tighten up the feather, the point on
They twist them in their lip.
twist them in their lip and stuff, and get a nice fine point so they could do high detail work. And so they were just wiping radium in their mouth. And there's a movie on it. I haven't seen it yet, but it's called Radium Girls.
Yep.
And I'd like to see it. I bet it's a nice movie. This is just a source of information. So they used these watches in World War II a lot because they wanted to be able to see what time it was in the dark. It would be the soldiers out on the front lines without turning on a flashlight, because for obvious reasons, turn on a flashlight when your enemy is watching, you might get shot. Radon gas is a decay of radium. We'll get into that a little more in a second. And Dr. Evans in 1933 was actually measuring radon exhaled by these watch dial painters. That's how much
That's a good concentration.
how much radon.
But you think about the natural radium that comes out of the ground, the basement.
Oh yeah, there's certainly natural radium, but I think they had a little higher than
No,
natural.
just a little more.
So, radon is radioactive. It's a gas,
Yep.
and it's an isotope 222. It has half-lives 3.8 days. When that atom splits, it gives off an alpha particle and turns into polonium-218 and lead-214. Those are not gases. Those are particulates.
Yeah.
And then each one of those radioactive decays in this series will give off different radioactive emissions, alpha, beta. And so one of the important things to remember is if you're testing for radon in your house, radon is kind of a surrogate
Yeah.
for actually the real hazard. Because radon's gas. Gone. Like that. Of course, you're exposed to it for hours, right? But what happens is the decay of radon produces particulates. Those are particles. Those will attach, as well as radon gas, to dust in the air. You inhale those, and then those may reside in your lungs, well, for the rest of your life, possibly, until you're able to expel those radioactive particles, however, coughing or maybe never. So those particles are actually more dangerous, and you test for radon because it's cheap and easy, but really what's going on is the particulates. Most people don't realize that, but this is really the surrogate. So if you have a lot of this, you probably have a lot of this,
Oh, yeah.
particulates, and that's what's going in. And this particular area, because we're near granites, you know, especially McCall and stuff, there's a lot of radon. So when one of those particles goes into your lung, again, it's an alpha emission. Alpha particles are large, and these are tracts of alpha particles emitting off a radioactive isotope element in lung tissue, and your lung alveoli are only one cell wall thick, and so it can really cause a lot of damage in there. And so those radon daughter products or progeny are bombarding your lung tissue with alpha radiation. So do you think we have radon in fossil collections down at Hagerman Fossil Beds?
Yeah, why not?
Yeah, just a little bit. So back in 1996, we had our first test done in a cabinet by John McBride. He measured an average of 436 units and a peak of 544 picocalories per liter. The EPA recommended action limit for your house is 4. So if you're 4 or above, they recommend, you know, putting in a fan, ventilating your basement, whatever you have to do, seal up the cracks. We had 400, so 2 orders of magnitude more, and that's in the cabinet. These are the actual results. This is a common practice of the paleontologists. These are all metal storage cabinets, and they're all sealed. And I know it gets better. And so they seal these cabinets because for proper fossil storage, you want to maintain constant humidity and temperature so your fossils don't degrade and crack and fall apart and all that stuff. But in the process of doing that, it locked all the radon inside the cabinets. And so we would have these high concentrations of radon in the cabinets. And you can see the radioactive trifoil symbol here on these cabinets here. We did some room tests just in the room, and in 2005, with a different instrument, we had 12 picocuries average. This is the data coming through here, and a peak of 26. It's still high. If you'll notice on the cabinets, this one here, you see a little silver feature here, and another little silver feature here, and the other cabinets don't have that, and another photo forthcoming. So early on, they were trying out how to evacuate the radon before you even opened the cabinet. So they put these valves on here that would fit a shop vac. So you shove the shop vac hose in the bottom and then run it outside and turn it on for suction, and then open up this one and ventilate the radon outside before you ever opened up the cabinet. That was a trial run. Nobody ever did it. They would just do this, and they never implemented this in all the other ones. It was kind of hard to do, and I don't know how effective it was. All This is another photo of the cabinets. These are all horse quarry. There's a feeding right there. Our test, we got some new testing equipment. And I was doing the testing at that time. You see the radioactive trifoil symbols on all these. They finally got that in. That wasn't until 2005. I started there in 96. So like 10 years later, finally got to this. Anyway, we bought a new in situ meter that we could put inside the cabinet and stuff. And so put it inside the cabinet, closed it up, and then I did my test. And we got like 150 picocuries per liter in the cabinet. So I called the manufacturer and I said, this doesn't sound quite right. We had some other tests that were like 400. Why did we get 150? He goes, well, we never anticipated our meter to be detecting or deployed in an environment where there would be in excess of 150 picocuries per liter. So we never designed it that way, and it actually had a governor or a threshold on the value. It wouldn't go any higher. We'd peg the meter.
That's disconcerting.
Yeah. Well, we didn't know either, I mean, I would have bought a different meter, model or something. We didn't know. We just bought a a real-time radon testing meter. So, yeah, you learn that stuff along the way. So let's see here. This is a study from the University of Iowa, where they demonstrated there's about a 10 to 20% increase in lung cancer risk with an average residential radon concentrations of approximately 3 picocuries per liter, and the EPA action limit is 4. I guess I don't see it there. Here it is here, 4.0 for EPA. So they're showing an increase in lung cancer at 3 and 500 or something.
Just a quick question. A couple slides back, when you did the initial analysis on the cabinets, the graphical representation down there, it seems like it's cyclic. Was it based on days?
Yeah, no. HVAC system.
Okay.
There's some cycle naturally in the environment where I know this was for sure in the room. So this was a room test, and so
like it would build up
this
at
was
night or
July.
something, and
This
then-
was July. So the air conditioner kicked on in the day, but at night none.
None,
So the circulation in the room.
yeah. Okay.
So there were some cycles from
All right.
some of that. Yeah, it's a good observation. Nobody's ever asked that before. But yeah, we saw those daily cycles move because, changing environment. Sometimes in the morning, people would come in and open the doors, and then pretty soon start ventilating and stuff. So there was.
So it just points up the importance of ventilation.
Yeah. Yeah, it's definitely important. Yeah. So Idaho has a connection to, we're now different topic, to the Plow Share program, or project, which was created by the Atomic Energy Commission back in the 1950s. Basically all the bomb makers were getting bored with building bombs and setting them off underground. That's no fun down around Vegas. It's like, can't we set them off somewhere else where it'd be fun, like, make harbors or mining, things like that, do something else with them. And so they had a program to go out and do stuff, set off nukes. And so they did it. And they conducted 35 nuclear tests and high explosives. That's where Idaho comes in, between 1958 and 1975. Seems kind of recent. Pretty amazing. But they had, the justification was mining applications, go down and set off a nuke and, extract your oil or whatever you're So, hey, let's build some new canals across the Panama area down here. Instead of just one canal, let's have half a dozen of them, you know, we only need 10 nukes, and there we go. So they were doing that, and this is actually Idaho. I don't know why they call it Nevada test site, because it is right here, 55 miles outside of Twin Falls. I'll show you a map here in a second. So in certain locations, instead of nukes, they used high explosives, and they wanted to find out if they used a nuke in fractured basalt rock environments, volcanic rocks, what would be the effect? So as a surrogate, they used high explosives, and that's what they did here. It's located clear down in this area of Idaho. And I put these Google Map coordinates on there, so if you want to take a look at it in Google Earth, you can find it. It's kind of hard to find unless you know where the coordinates are. But it's still down there today. You can go picnicking down there if you like. There's this organization, Desert Research Institute, finally, I didn't mean to say finally, but recently issued a report on that site back in 2011. And there's some markers. There's a lot of stuff down there still. It's not just the big hole in the ground. There's, you know, all the observation booths, and, you know. So they drilled some, I put this in here because I did a presentation for water resource. They drilled monitor wells to see what would happen to groundwater and things of that nature. So they drilled wells and all kinds of monitoring systems that were in place. And then a time series of going off. When they constructed this, I don't think I put a photo in, it's kind of interesting. They didn't just dig a hole and dump it full of explosives. They went in and kind of mined out a shaft, a vertical shaft, and then a chamber, a round chamber in the subsurface. Then they filled that chamber up with liquid nitrogen-based explosives, ammonia rather, and then they fused and ran. And so, anyway, it was an engineered explosion, not just a haphazard. You know, they did it quite structured. But anyway, this time series thing. So, I've always been told go out with a bang, and so I did, and that's the end of it. And it's just an air photo from 1967. It's still down there, and one of these days I'll get down there. I think it's a real rough road going in.
Well, it's good geology trip.
Oh yeah, be excellent. And there's other stuff. You'll see roads going everywhere and structures, and I don't know what they are, but I'm sure they're associated with this explosion here. So.
I'm assuming BLM land, was it?
Yeah, BLM. Yeah. So now you know why I have a radiant complexion. And I've lost my hair.
That's why we had to scan him before he came in and give the talk. Let me ask you a quick, you know, if I went out and I picked up that peccary tooth at 21,000, put it in my pocket,
Yeah.
and I walked around all day, what would happen?
Yeah, I don't know, but you probably wouldn't want to do that. Yeah, you don't want to sleep with it underneath your pillow or something.
Well, how long would it have to be in contact, close contact like that to really cause damage?
I can't answer that specifically. I'm not a hygienist. And so that's where Dr. Ron Catherine and other folks would come into.
Well, it depends what it's emitting, whether it's a surface active or an internal. Or
Yeah, and you'll get all three emissions, alpha, beta, and gamma. So it's going to penetrate. I'm just presented, we used a Geiger counter. It only detects 30% of the beta.
Mhm.
So all the gamma and, it's not detecting that.
And then how much
And
of it
the
go
alpha
through
is,
clothing? or
breathing
whatever?
in primarily.
Yeah.
One of the, so you might surmise, well, so if you have fossils, you need to prep them out, right? You gotta get the matrix away from the bone, and it's like concrete. do that.
Drill.
That's exactly right.
Aerosolize.
And it's, they just use miniature jackhammers, air scribes. They sit there and
Yep.
And so when you do that, now you have a combination of a
That's-
bunch of radioactivity,
Mhm.
radon gas, and dust particles. And so it was a huge issue and hazard down there. It wasn't until just, I think, 2 years ago now, they finally got a brand new fossil preparation facility built to deal with it. 2 years ago, 2020, we knew about it in 1996. I spent years doing this stuff. So,
Yeah, you can go to John Day and look at their preparation area. It's just open air. The one up in Alberta, same thing. You can look at their prep area through the glass, and it's all just open air. There's no windows.
yeah.
I think they have, I've seen like they have a fan that's sucking air right above the repair.
Yeah, yeah, they finally got a ad hoc type of ventilation system. I mean, we had a contractor come in and build some preparation booths. This would have been about early 2000s. And they put in a big ducting system to suck the air out and dust out outside and stuff. So they were making some efforts all along the way, just like the ports on the storage cabinets. You know, they did that and they did this and stuff, but they didn't get a new facility to fully exercise all the safety protocols until just 2 years ago. So there was efforts made along the way, but they were temporary because they were in temporary structures and facilities. And it was an old farmhouse where they were at one time. But so it's quite amazing to me that it took that long.
When radon decays, it becomes a particulate,
Yeah,
and then it attaches itself to dust, or how does that work?
yeah, yeah. Yeah. And the particulates themselves, the radon, the little dust particle, you know, your cat dander, whatever, just radon attaches to it. Then it'll go in, if it resides there for a maximum of 3.8 days, could be shorter, then it decays and splits.
Question on the horse site at Hagerman. So is it still open for them walking around and?
No, they've always had it controlled, so you can't just go out there and wander around and go, yeah, go down there today. So they used to just do scheduled tours, which is basically a form of controlling people in and out. A little backstory, you might wonder, so what did the Park Service do with all the stuff, overburdened and broken fossil chunks that they removed with the backhoe? What'd they do with it? Well, they moved it all around the corner first. So they came in and cleared it all, and included all kinds of stuff. It was in big piles around the corner. And I was working there, and the summer paleontologists were working there in the summer. Park Service wanted to bring public and tour groups up to show them, because they now had the bone bed exposed. And so they did that. But they also knew that in those piles over there was a ton of stuff, fossils. And so what they actually did was they had radios, and they would coordinate between the field paleontologists on site and the tour guides coming up with the public, in, a bus or something. And they say, all right, yeah, we're coming up, we'll be there in 20 minutes. So when the public was present, they'd all be over there on the bone bed, scratching and taking pictures of, stereotypical stuff that looks good, and then as soon as the public left, they went around the corner, got their screens, and started sifting all the debris piles for the material. they screamed out like a backhoe. Then another tour group, they run back over, all look good. That's exactly what he did. Oh, I've got tons of stories if you want to keep going. Want to hear the beaver story? I think you saw some beaver vertebrae there earlier. So I was directly on that one, late 90s, 98 range, 7 maybe. So we found some articulated beaver bones in outcrop. Looked like, you know, the rest of the beaver was present in situ or in place and articulated. We were like, woohoo! And you know, the whole beaver here, we just need to excavate it out around it. You know, so we did, we pedestaled it, you know, turned it into a toadstool, mushroomed around it, plaster casted it. You know, the cast was huge, literally huge, you know,
Giant beaver.
5 feet by 4 feet or something, monstrous thing. Huge cut in the side of the hill, you know, and we were like, all right, now how do we get this out? It weighed about a ton. I think it was half a ton, 1,100 pounds. So we tried to drag it out. Well, that was fruitless. With all the horsepower we had. And so we were sitting there going, all right, how do we get this out of here? I know. We'll get the BLM fire crew to do a practice run with their fire crew helicopter. That's exactly what they did. So they called up Shoshone BLM and said, hey, you guys want to do a little practice for your firefighting crew with the helicopter and come down and help us fly this thing out? So they built a special pallet for us made out of oak for strength. Put down a big net, and so they put the cast on the pallet on the net. Called up the Times News. They had a big fanfare because there's nothing more exciting. I have another word I commonly use, but I try not to use it. But nothing more attractive and exciting than, you know, a beaver being flown out across the monument, across the Snake River, through the sky in this big net. They drop it down on the back of the truck, and we hauled it all back. And there's all the fanfare and the photos and the live KMVT video and everything. What do you think happened? So we had a volunteer working on it, sitting there scratching away. And this wasn't in a sand unit, so this one wasn't radioactive. And so volunteer spent probably 6 months or more sitting there scratching away. And I talked to her one day and I said, so whatever happened to the beaver specimens? She says, you didn't hear? I said, no, what? Because I was working on other stuff. There was no beaver in it. All it was the bones we saw. Oh, no. It was all dirt. We flew out a big cast of dirt. Yeah. Follies. Yeah, you guys don't. You don't
You're
know.
Jack's
You don't know this. You do not know any of this stuff unless you work on the inside circles. Yeah. Where do I end? I just keep going.
Well, why don't we bring this to an end? If Neal can stay around a little bit for a little more discussion, but let's give him a nice. We'll keep the museum open. If you'd like to take a look around, those that are not members or haven't been here before or haven't seen some of our newest exhibits like coyotes, Native American use of mineral resources.
I have to come look at my.
Please feel free, and the gift shop will be available for your Christmas shopping pleasure. So, thank you very much.
Thank you.